So it's time now to speak about the quantitative analysis and the last part of this outline on chromatography. So this is on the qualitative and quantitative analysis. So what is the qualitative aspect? The qualitative aspect is, of course, the most simple aspect in analytical science and particularly in chromatography, because it just consists to identify a compound. It is only, the only aim is to know if the compound is in the sample or not. So to perform that in chromatography, we obtain the results on the retention time, and then we compare the retention time with standards. It means that if I have the separation of 3 or 4 compounds, for example, in a sample, I don't know, I have a peak. If it is, for example, in UV, I just have a peak, and then I don't know if it is my compound or another compound. Then to be sure that this is my compound, I inject standards, so the same molecules, but I know that this is the same molecules, and in the same condition with the same column and the same mobile phase, I will have the same retention time. Then I compare these two retention time, and if the retention time the times are similar, and then I consider that this is the same compound. I can then determine the retention factor K prime and the selectivity alpha. But sometimes we had issue about the standard, because sometimes it is not possible to obtain the standard of our molecules. And then if the comparison with standard is not enough, or if it is not possible to obtain the standard, some detector may additionally provide information on the nature of the product. You have, for example, mass spectrometry, because in that with mass spectrometry we have the molecular mass of the compound, and then we have structural information, and you also have the NMR detection. So no ambiguity regarding the nature of the detected compound, because with this kind of detection we have structural information, and with structural information we can of course give all the information about the compound. So the difference between qualitative and quantitative aspects is the fact that, of course, the quantitative aspect of a chromatography consists of identifying the compound, but also quantify it. And that's, of course, more difficult to perform, because in that case, first you have to perform the qualitative aspect, you have to identify your compound, but you also have to give the quantity of the compound in the sample. So for UV detector, it is assumed that there is a linear relationship between the area of the chromatographic area, a peak, and the amount of compound responsible due to the Beer-Lambert law. So the amount of product injected into the column is distributed over the entire surface of the chromatographic peak. And then the calculation of the sample quantity is done by integrating the area. And here you have the relation with, of course, the different integration of the area of the peak. The area of the peak is proportional to the quantity of matter than the quantity of the molecule. So here you have the representation of the integration of the peak. So the representation of this equation, you see the peak, the Gaussian peak, classically obtained on a chromatogram, and you see that we integrated the surface of this peak, and all the surface of this peak are proportional to the detected quantity of matter. So the drawback, of course, is the fact that the value of the response coefficient K, which is here, which links the surface to the quantity injected, is not known. We don't know the value of this K, because of this constant K. If we know this value, it is very simple to give the value of the quantity, but the major issue is that we don't know this value. We have to determine it using using a calibration standard. So, as I told you, how to quantify a compound. It is possible to quantify a compound if we use the calibration technique. And this calibration technique allows us to obtain the value of the constant K to determine the concentration of our compound. It is possible to use different techniques of calibration. Here I show you only the two major calibration techniques: the external calibration and the internal calibration using an internal standard. So the first one is the most simple calibration. It corresponds to the external calibration. We have the principle of this calibration. We use standard solution, and standard solution are injected at different concentration. Then we perform the representation on the area in relation, so in function of the concentration of the standard. So here you have the different concentration, and we have the different value of the area. We trace the regression, regression lane, and then we obtain here, if it is good, we obtain the measured peak area of the unknown compound, and we can calculate using the equation of the lane the concentration, the unknown concentration of our compound. So of course there are limitations to use external concentration, because you need to be sure that the area is proportional to the concentration. And sometimes this is not the case, because there may be problems of repeatability of the injected volume. Indeed, the area is proportional to the quantity of matter, but the concentration is not the quantity of matter. The quantity of matter is the mole number, and is equal to the concentration times the volume. Or if the volume, the injected volume, is not constant, there are no repeatability, and then this is not proportional. So in that case, we use standard. In that case, we use another calibration, which is internal calibration. There are another limitation, which is the standards, because standards are essential and may be unavailable commercially. In that case, you use some other detector, like mass spectrometry, for example. So you have the possibility to use internal calibration to correct the injected volume. The major issue of external calibration is based on the non-repeatability of the injection. Indeed, if you don't have the good injection, you see that the area is not linear. So as a result, we perform the calibration curve, and this is not exploitable because unrepresentative. So to correct this, the solution is the internal calibration. What is the internal calibration? Here you have the internal calibration nomenclatures. So we use an internal standard, HE. We use an unknown. We have an unknown sample, so the sample, and we have the standard, of course, used in the external calibration. So the only difference is the presence of an internal standard. So the principle is to use an to use an internal standard at a fixed concentration on all the solution. So we use this internal standard. We optimize the separation of the two compounds, internal standard and the unknown sample. We achieve the calibration curve varying the concentration of the standard and keeping a fixed concentration of internal standard. And after that, we represent the calibration curve, which is the ratio between the area of the sample and the area of the internal standard in function of the ratio concentration of the sample over concentration of the internal standard. After that, we perform the calibration curve, and then we inject the mixtures containing the standard, the internal standard, and our unknown sample. We reverse the measurement value on the curve and deduce the unknown sample. So, in practice, here you have the standard solution and the not standard solution, I'm sorry. And here the internal standard solution, you see that we have 5 different solutions in the in our curve, for our curve. Here you have different concentration of the standard. So this is 1, 2, 3, 4, 5 milligram per milliliter. And here you have always the same concentration for the internal standard, which is 1 milligram per milliliter. We perform the separation of the 2 different compounds. Here you have the dead time with the solvent, and our 2 different peaks, a big separation, a good separation with a good resolution. The internal standard has a constant area because he has a constant concentration. So you see this is quite similar for these peaks. And for the standard, you have an increase of the area because we have a gradient of concentration. After that, we perform the representation of the ratio, area of the standard on area of the internal standard in function of the ratio of the concentration standard over internal standard. Different point, different concentration, and then here you have a good linearity with this regression. Then after that, I measure my unknown compound. We have the area of our unknown sample on the area of the internal standard, and we deduce, of course, the concentration of our unknown compound by this equation, this simple equation, using, of course, the equation of the curve. So the internal standard has some properties. The properties of the internal standards are to be very close chemical structures as compared to the standard, to our molecules, because you need to separate this compound, but of course without any too much separation, too much time, for example. Very close retention time, because of course if you have a separation in 2 hours with just the internal standard, there is a problem of analysis time, and very close concentration to calculate the good ratio. The purpose of using an internal standard is the use of a concentration ratio and to correct the volume repeatability errors. That's very important.